There he is, Joseph Fourier, rather serious looking on this tombstone that you can visit on your pilgrimage trip to Paris in the Père Lachaise cemetery. So this is the cemetery where also, you know, the singer of Doors and other people lie. But you know, this guy here, he's worth visiting. He was an interesting person. So he was born into a normal family, and so not rich, not wealthy, and he was quite active during the French Revolution. So he was born 1768. So he was around 20 when the revolution was raging, and he played a role in that. He even managed to survive the terror when good people were guillotined left and right. And because Napoleon was impressed with him, he took him on his crusade to Egypt and made him a prefect of Lower Egypt. You know, not many people have held that title, I think. And but even before he went, he had already been appointed mathematics professor at one of the Grande École at age 28. And then, well, when the British retook Egypt, he went back to his university in France. But Napoleon wanted him as a governor in the Isère district, which is Grand Grenoble, where he. So if you drive these roads nowadays, there will probably be some that are going back to his planning. So he did that, and while he was there, he started his experiments on heat diffusion and wrote his treatise on that. And it is these studies that we owe the Fourier transform to. So not all mathematicians are boring. It's the bottom line here, if you've ever believed such a thing. Okay. Now, why do we talk about the Fourier transform? Because the Fourier transform is unique among all unitary transforms because it diagonalizes all shift invariant operators. As we will soon prove. But why care about such shift invariant operators? Because they too are universally useful. So LSI or LTI means linear shift invariant or linear time invariant operators. So they are useful in many fields, for example, in engineering, because you can simply treat this as a black box. So you have a black box. This is your LTI system. And the nice thing is that you can learn everything there is to know about this box by putting in a single impulse and then listening what comes out on the other side. And it turns out that, you know, from what you've listened to, that this tells you everything there is to know about this model. So let's look at the letters in LTI. Linear means that if I have an operator A, which I apply to alpha times a signal G, so G is again a vector and alpha is just a number. then this is the same as that. And also if I apply this to the sum of two signals, the result is the same as applying the operator separately to the constituent signals. So that's linear. And then we have time invariant, which means the system never changes. So if we have that the output of applying operator A to G is called H, then if I apply instead my operator to a shifted version of the signal, then the output will be similarly shifted. I can index the shift operator with a lag L if I want. Both of these postulates are fictions when it comes to real-world systems, because a system is never, so there is no system in the world which is linear over all inputs. So it's never linear. Can you explain why? Yeah, any sensor you have, you saturate eventually, or if you want to, make this argument more extreme, you can burn or kill any system by putting in too much energy. Yeah? So if I make this peak here, higher and higher and higher, eventually I get, smoke. So in this sense, bear in mind that no system in the world is truly linear. And then also, no system in the world is truly time invariant. So why is every real system time varying? Yeah, but you could have systems in equilibrium with the environment, but the point is that our environment is of finite age also. So at least most people in this room believe that the universe is of finite age, and that implies that the system didn't exist at some point or must have had different properties at some point. Okay, so take it as a joke, but the point I want to make is that it's a very useful model, but it's just a model for these two reasons and others more. In the real world system, you have nonlinearities and so on. Okay, and actually, these two properties are already enough to argue that any linear time invariant system can be fully characterized simply by its response to a single impulse, as I showed in this sketch. Because I can write an output as A times G, and now I can decompose G. I can say that this is a sum over weighted impulses. So delta J is an impulse located at position J. And then by linearity, I can write it like that. And that in turn results from applying a shift operator to impulse sitting at 0, which shifts this impulse to position J. And I can invoke linearity once again And this quantity here, that is the impulse response. So any signal can be modeled as a weighted sum of shifted impulses, and once I know the impulse response, I can reconstruct the response as a weighted sum of these shifted impulse responses. And this taking the weighted sum of shifted responses, that amounts to doing a convolution. So if I look at just the jth element of my output, so this delta here, this was a vector. And if I call this impulse response A, then I can say that this is sum over J, Tj, then comes my shift operator. And then my impulse response. Oh, I need a different index here, sorry. Like that. This I can rewrite as a shifted version of A. So this is A at L minus J. Now you see I have a plus J here and a minus J there. And this altogether is a convolution. So I can say that the output of an LTI system is given by the convolution of the input and the impulse response. It's important enough to box the statement. I've been a bit sketchy with where exactly the summation starts and where it goes to. The reason is that we need periodic boundary conditions, and I didn't want to talk about this complication now. Or we need periodic boundary conditions if we want to use the discrete Fourier transform. So, well, in this simple model system, this model class is vastly popular because it is approximately valid in a large number of cases. So at least for a certain range of inputs, many systems can be modeled as linear, and it's super simple. Because this impulse response encapsulates everything there is to know about the system at hand. Any questions so far? Okay, I then want to talk about the matrix way of expressing these things. So LTI operators in matrix notation. And there the devil is in the details, and we'll get to these now. So again, I call the output H, and that results from applying operator A to an input signal G. And if I now insist that I want, for such a signal of finite length, that I want shift invariance, then I can only achieve this if I use periodic boundary conditions. That I use in my convolution. So I'm going to use, in fact, a circular convolution. And that means that the structure of this matrix is a special one, namely A is a circulant matrix. So a circulant matrix is defined as follows. Each row results by shifting the previous row by 1. This is what also happens in any triplets matrix. The difference to any triplets matrix is that here we're using these periodic boundary conditions. So if something exits on the right-hand side, then it comes back in on the left-hand side. So let's look at a concrete example. The central finite difference operator. I'm going to apply to a signal of length 5. Let's call this D for short. And I'm going to use C-style indexing. So the first element of a vector has index 0. We have G0, G1, G2, G3, and G4. And if I now use or insert a single impulse, so using as input a 1 in the first position and 0 everywhere else, gives us the impulse response. We essentially read out the first column of this matrix. Okay, now this thing is a bit tricky here because, if you look in this direction, somewhere in the matrix horizontally, we have -1, 0, +1. But if we look along the columns, then we have +1, 0, -1. And this matters. If you have a mistake here, you estimate the slope with the wrong sign. So let me write down how this works more generally. I use as the first column my impulse response. And then the second column results by shifting. and so on. So this would be the circulant matrix that represents a convolution with impulse response A, where I define the first column here to be A. And from the property of matrix multiplication, we can derive a couple of rules. So matrix multiplication is associative. I can interpret B times A times G as either BAG or as BAG. And if I write it in terms of convolutions, this tells me that convolution 2 is associative. Okay, and this is a useful rule, for example, because if you want to apply multiple filters to your signal, then you can, for example, first compute what the combined filter looks like, and then use that combined filter just once, rather than running separate operations here. A little bit less easy to see is the commutativity, which does not hold for general matrices, but does hold for circulant matrices. So A, B, G is the same as BAG for A and B circulant. So it means the order in which I perform a convolution also does not matter. It's another practical thing that you find often in work. Okay, so there was a mini introduction to linear time invariant systems. So the thing that's most important to remember is that a linear time invariant system is fully, totally, completely, exhaustively characterized by its response to a single impulse. It is implemented by convolution and can be represented, if the signal is a vector, then it can be represented by a circulant matrix. Okay, now I started off with the claim that what makes the Fourier transform special is that it diagonalizes any shift invariant operator. So the eigenfunctions of any LSI operator, no matter if it's something that computes the slope or the curvature, or if this is a smoothing filter or a high-pass filter, its eigenfunctions are always given by the Fourier basis functions. I've just been mentioning a few examples, and perhaps I should write them down. For example, if you want a bandpass, you want to filter out the low frequencies and the high frequencies, this would be an LSI system. Or if you want to discard all the high frequencies, if you have a low pass, this would be an LSI system. Or if you want to compute the derivative or the curvature of the signal, this and many other are linear shift invariant operations. And they do very different things. So it seems quite magical that they should all have the identical eigenfunctions. Now, I've already given away that it's the Fourier basis, or you knew beforehand. But in the days when there were no textbooks telling you that, how would people have found out? And well, so what's meant by eigenfunction is that if I'm looking at if I have some operator and I apply it to to the kth eigenfunction, then I want the result to be just a complex constant times that eigenfunction. And the complex constant, the eigenvalue, I will call it differently here. I will call it this later on to stress that it comes from A. So let's say, assume that so I'm going to proceed by counterexample. So for example, I can consider a pure shift operator. Then I could say the input to my LSI system would be an impulse sitting here at position 0, and the output would be a pulse that comes out a little bit later, perhaps at +2. And now these are vectors, so I could have, or I should have shown these as discretely sampled signals, because this is our assumption here, that we have discrete signals of finite length. And by looking at these, you can see there's no way that a constant times the one will give us the other. So taking a pure shift operator as an example tells us that a single impulse or anything composed of a few impulses won't work. So if I have a small set of peaks here, I will shift the small set of peaks. I will, anyway, again, one is not a multiple times the other. So we want something that is mapped onto itself by a shift operator. And I don't know if I would have had that idea, but it makes sense to use something periodic. Okay, so because if the input is finite, then a shift operator will give you the result that I've shown. If you have a periodic input, there is more of a chance that the output may look similar to the input. So let's take, for the sake of argument, a simple sign. So let's say I'm taking a shift operator which induces a lag L, and I am applying this to I'm using continuous notation here, the sine of x, continuous signal, not a discrete signal. Which is this, which I can represent as alpha times, there's a phase shifted sine, alpha times sine of x plus beta times cosine of x. And alpha and beta are a function that I've forgotten of L. Now again, this is not quite an eigenfunction. Here we have the sine, and here we have the sine plus cosine, but it's getting there. And of course, you all know the answer. The answer is to try a complex in dimensions 2 or higher. I would call it a complex plane wave. So Fk of L is that, with L being an integer number between 0 and n minus 1, the length of our signal. So this is a discretely sampled signal, and because I'm having a minus I times the sine, it's a spiral that's going around like this. And we're having a discrete signal, so I'm only sampling this spiral at finite intervals. Okay, so all of this, what I'm trying to draw here, is Fk for a given length of 20 points or so in this case. So let's see if this does the job. If I convolve A with Fk, and I'm looking at entry number L, I'm spelling out this convolution now. Sorry, I made a mistake. This should be a plus, this should be a plus, and the spiral is going the other way around. Sorry, I do need a plus here to end up with the normal convention, which is a convention, but it makes sense to stick to it. So here I have plus j, and here I have L minus j, making this a convolution. And I can now pull out the part that is independent of j. So this is I 2 pi over n kl. The minus from the j I've put here in front. Overall, we now have something that only depends on k. And if we look at the definition of fk on top of the page, we now see that we find back fk here at the position L. In other words, we have this time truly found an eigenfunction, and this is the eigenvalue going with it. Okay, so we see that these complex plane waves or complex exponentials, they are indeed eigenfunctions of any convolution operator. And the eigenvalues are given by the Fourier transform, because this is what this line here is, of the point spread function. And after the break, we will spend much time looking at the properties of this in more detail. Okay. So next, I want to do two things. I want to try and give you more of an intuition for what this Fourier transform is that we saw here at the very end of the last hour, and to again establish the relation with the matrix notation. So we're looking here at the convolution of A with Fk, and all of this quantity here is the eigenvalue, which depends on k only. And this is the name that I've given it, A, because the operator, the associated operator, is called capital A. Now this is a complex number, and it has two properties. The magnitude tells me if I look at my input in terms of such complex plane waves or complex exponentials. I've shown you a prettier picture here at the bottom. They are of different frequency. So this is Fk now with the proper sign convention. And this is here for a k of 3. So this is, rather than Fk, I could also say this is here F3, if I'm saying this goes here from 0 up to 1. And the magnitude tells me how much each frequency, and k is the index for frequency, how much each frequency is amplified or attenuated. So the magnitude already tells us that if this is something larger than 1, this can actually amplify. If it's smaller than 1, it only dampens. And then we have the phase, which tells us by how much signal component with this frequency is shifted So it may be that some frequencies get delayed more than others by a specific operator. And here's a prettier picture than I drew by hand. So blue is the real part, the cosine. Red is the imaginary part. And this complex vector is represented by this spiral. So I want to look again at what this has to do with matrix notation. So we're looking at the convolution of A with Fk. Looking here at element L of the resulting vector. And I'm now exploiting the fact that convolving A with F or F with A is the same. So I'm now using a different convention from above. So here I sum over AL minus J, Fkj, whereas further above I had summed over AJ and FL minus J. You know, it's identical or equivalent. So let's look at this for explicitly for L equals 0. This is a representation of an inner product. The first element, when setting L to 0 and J to 0, is A0. The next element is A minus 1, A minus 2, and so on. And Fk is a vector, a column vector. But now I'm exploiting this periodicity, and I'm rewriting this as A0, then A minus 1, the same as AN minus 1, because I want my signal index to live within 0 and n minus 1. This is the same as n minus 2, and so on. And the last entry is A1. And I'm now writing down explicitly also this eigenfunction here. So this is for L equals 0. And if I now scroll back to the definition of the circulant matrix A, which we hit somewhere last hour, there. Now look at the first row here. The first row is exactly what I now have down here. And if I choose not L equals 0, but L equals 1, I will find that I get the next row of the matrix, and so on and so on. So in other words, this is indeed the same as my circulant matrix A multiplied with the vector Fk. So overall, I find that using the matrix, or this time I'm usually omitting the circle, but this time I'm writing it properly to say that I'm here talking about the circular convolution with periodic boundary conditions. This is the same as eigenvalue times eigenvector. And to this eigenvalue, I've given a special name. I've called it A with a circle on top to indicate that this comes from the transform of A. Okay. The only thing that we required of A was that it must be a circulant matrix. So these complex plane waves, as is appropriate to call them in higher dimensions, they are indeed, as I had claimed before, the eigenfunctions of any LTI operator. Okay, now, so far I said that here K and L can be any natural numbers, but since I have this periodicity, if I make K or L too large, they're indistinguishable from the smaller values from the first, what in physics would be called the Brillouin zone. Okay, so in particular, FKL is the same as FK plus NL, which is the same as FKL plus N. Now to get rid of this redundancy, so to obtain a basis that is both complete and non-redundant, let both K and L come only from 0, 1, and so on, up to n minus 1. And for these values, what we get is the Fourier basis. And I'm going to collect all of these vectors in a matrix F, which is here stacked together, F0, F1, and so on. And before, we had always looked at a single eigenfunction at a time. If I want to look at all eigenvectors simultaneously, I can say that AF equals f a circle, where this is a diagonal matrix. Holding along its diagonal this vector of Fourier transform coefficients of the impulse response. And since it's acting from the right, this reweighs the columns of f. Now the basis that we have chosen is unitary, so I can, if I want to isolate this diagonal matrix, I can multiply from the left with the f adjoint, giving me this. And there's one final thing missing. For a unitary transform, we want the vectors to be not only orthogonal, but also normalized to 1. And right now they are not. So for example, if you consider f0, which is just a vector of 1s. So if I compute f0, transpose f0, the result will be n, but it should be 1. So I need to normalize by the square root of n.